in this example, I want to look at this matrix. It's the same matrix that we started with in the section on eigenvectors and eigenvalues. It's really a reflection, but it looks so much more complicated than that. We've already found that these were eigenvectors, so I want to look at this relationship a tiny bit more. So I want to look at the linear transformation, that's multiplication by A. So really I want to look at that reflection, but I want to look at the matrix representing this reflection in this special basis. Alright, so we know how to do this. We need to take this vector, apply TA to it, and then rewrite whatever the image is in this basis. So let me write it like this, and then I have to do the same thing. Minus 4, 1. Again, I want the coordinates of that vector in the original basis. Alright, so TA of 1, 4, that's A, so minus 15 over 17, 8 over 17, 8 over 17, 15 over 17. I'm going to multiply this by 1 and 4. What I'll get is minus 15 plus 32, so that's 17 over 17. So I get 1. Then I get 8 plus 60, and I get 4. Alright, so the vector TA of 1, 4 is again the vector 1, 4. Now to get the first column, I need to write this vector as a linear combination of my basis, and then the coefficients in front, those will be the numbers in my column. So I need to write this as a linear combination of my two vectors. Well, that's not too hard because it's exactly the first one. So I'm going to take 1 times the first one and 0 times the second one. All right, so that first column will be 1, 0. All right, TA of minus 4, 1. Again, let's just multiply. I get 60 plus 8. That's 4. I get minus 32 plus 15. That's minus 1. Alright, so again, to get the numbers in that second column, I'm going to have to write this as a linear combination of my two vectors. So we had 1, 4 and minus 4, 1. Well, it's almost this one. You just have to multiply it by minus 1. Alright, so we have our numbers. The first column is 1, 0. Second column is 0, minus 1. And so we get 1, 0, 0, minus 1. What we like about this is we get a diagonal matrix. we've been thinking of how to diagonalize matrices, and we've been talking about finding the right basis. Well, for this matrix, the right basis is 1, 4, minus 4, 1, or one of the right bases is 1, 4, minus 4, 1. And really it has to do with the fact that these vectors are eigenvectors. All right, so let's do a tiny bit more. In the definition of diagonalizable, we talked about A and D being similar. So we need that matrix P that will transform A into D. So I want TA, and I'll call it D because now we know it's diagonal. So let's put a big, oh, still black. Guess that's fine. I want to find P so that this is P inverse AP. So I've already mentioned that you should think of P as a change of basis matrix. In this case, it looks like we only have the special basis B, but we also have the standard basis. So if I take S to be the standard basis, then if I look at the basis representing TA in this standard basis, I would just get A. All right, so we have TAS is equal to A, and if I take B to be, what was it, 1, 4, minus 4, 1, then TA in the basis B, that's my diagonal matrix D. So if I look at the standard basis, I get the matrix A. If I look at the special matrix, I get my diagonal. Special basis, I get my special matrix D, which is a diagonal matrix that I want. We've already talked about how different matrices for the same linear transformation differ by a change of basis matrix. So what I'm going to take I'm going to take P to be the matrix that takes us from S. Wait, is it B to S or S to B? Let's take B to S, sorry. And so we've already talked about this, but it might be a bit far, so please, at this point, if you're getting a bit confused, don't hesitate to pause the video and go back to that section on linear transformation and what happens if you use different bases to represent them. All right, but what we have is that if you want to have the linear transformation TA in the basis B, then you can start in B and go to S. In S, you can apply the linear transformation, and then you need to go back, and so that means P, B to S, S to B. And now you're back in the basis B. All right, so you go from B to S. You apply the transformation in the basis S, and then you go from S back to B. And that's going to give you that D is, this is P inverse, this is A. All right, so let's find P in this case. That again, we'll use your memory a bit. So P is linear transformation from B to S. And to find that, you take every single element of the basis B, and you write them in the basis S. Now, in this case, we're not lucky. This is not particularly a challenge because the last basis, S, is just the standard basis, so we don't actually have to do any work. The vectors come in the standard basis. So we had 1, 4. 1, 4 is 1 times this, plus 4 times this, and then minus 4, 1. Let's check that this is true. I'm going to compute P inverse AP. I'm going to use the formula for inverse for 2 by 2, so 1 plus 16, so 1 over 17. And then I'm going to switch the signs. A I don't have anymore. Let me look at the notes. It's minus 15 over 17, 8 over 17, 8 over 17, 15 over 17. Let me just write P here so I can come back to it later. Here I have 1 over 17, minus 15 plus 32, so that's 17 over 17, that's 1. Here I have 8 plus 60, so that will be 4. Here I have 8 plus 60, that's 4. I have 60 plus 8, I have 4 again. And I have a minus 32 plus 15, I have minus 1. And then I want P. P is this, so 1, 4, minus 4, 1. I get 1 plus 16, I get 17. Minus 4 plus 4, I get 0. 4 minus 4, I get 0. Minus 16 minus 1, I get minus 17. So I get 1, 0, 0, minus 1. Excellent. All right, so this works. It's still a bit complicated. I don't want to have to think of all of these facts. I don't want to have to think of change of basis, how to construct the matrix this way, this way, this way. So what we'll do next is we'll come out with a systematic recipe for it, and we'll have a theorem that tells us when we can do it and when we cannot.